Good day everyone, my name is SITI NOOR Arifah binti Sheikh Fizrulsha, but you can call me Ari. My matrix number is B142510011. For our CAD project, we chose to reverse engineer a toy called a Bidaman. Bidaman models are excellent for engineering study because they combine complex organic aesthetics with precise mechanical functions. Our goal was to take a physical toy and recreate it as a functional 1:1 scale digital assembly in SolidWorks. Using a vernier caliper for data acquisition, we focus on ensuring that the firing mechanism, the heart of the model, the core, was modeled with high accuracy to allow for realistic movement and interaction.
Hi, my name is Muhammad HAZIQ, matrix number 142510.
Matrix is B1425100.
Hi, my name is Muhammad HAZIQ, matrix number 142510. For this project, the objectives are divided into 5 main parts. First, to study the mechanical design of the Bidaman Drezeros. This includes understanding how the main components are arranged, how the launching mechanism works, and how force is transferred during shooting. Second, to develop 3D CAD model of the Bidaman parts and the full assembly. Each component is modeled accurately using CAD software and then assembled represent the complete structure of the toy. Third, to carry out simple simulation on selected parts. These simulations are used to observe basic stress distribution and deformation under applied loads. Next, to analyze simple design improvement to enhance performance and durability. This improvement focus on strengthening critical parts and optimizing the design without increasing complexity or cost significantly. Thank you.
For this part modeling strategy, all dimensions were set in millimeter to ensure accuracy and consistency throughout the design. The main shape of the part was created using the extrude boss or base feature. This was used to form the structure core of the compartment, so that is strong and stable. Fleet was used to model the organics and acoustic curve, especially on the headpiece and wings, to achieve a smooth and natural shape. Lastly, fillet will add the shaft angle. This helps to make the parts look more like plastic model product and also reduce stress concentration, which improves durability. First, we discuss and decide what project we want to design. After that, we select the Bidaman as our product. Then we analyze the Bidaman and separate it to the many parts. This helps us to understand how each compartment works and fit together. Before start 3D modeling in SolidWorks, we create a hand sketch, and the sketch were used to plan the shape, size, and the structure of each part. This made the 3D modeling process easier, faster, and accurate. After the sketch, we make a 3D part from SolidWorks, and we need assembly all the parts to one product. Then this is our assembly view.
Looking at the exploded view, you can see the complexity of the assembly. It consists of 12 main components. At the center is the core, which houses the primary firing mechanism. Notable parts including the trigger, the spring, and the shoulder which work together to launch the marbles. This view highlights the modular nature of the design. The wings and the head are separate components that snap onto the core, which includes the arm as well. Modeling these separately allowed me to manage the assembly's hierarchy and ensured that each part had the correct mechanical mates to move as intended. You can see which from the three of us is responsible for each part based on our report. What we learned from this project is it centers on the challenge of reverse engineering. The most difficult part was translating the injection of molded plastic shapes into parametric sketches. Unlike standard machine parts, the Betaman has many curves, aerodynamic surfaces, so we had to balance the precision of our vernier caliper measurements for the functional slots and pins with the artistic use of splines for the outer shell. A key discovery during this process was the importance of clearances. We had to manually adjust our measured dimensions by roughly 0.15 millimeters to ensure that in a real-world scenario, the trigger wouldn't seize up inside the core housing. To validate the model, we utilized the assembly visualization and interference detection tools in SolidWorks. In this view, you can see the model color-coded by mass properties and volume distribution. This allowed us to identify where the bulk of material is concentrated, specifically in the core and legs. It's to ensure that the center of gravity remains low for stability during firing. We also run interference checks to confirm that the marble, which is the blue sphere, has the correct tendency with the barrel. This analysis confirms that the digital model isn't just a 3D picture, but a mathematically sound mechanical assembly. In conclusion, this project was a valuable bridge between classroom theory and practical application. By rebuilding our Betaman from scratch, we moved beyond basic part modeling and into the territory of assembly design and mechanical thinking. While we encountered challenges with the measurements, errors, and complex geometries, the final result is a high fidelity model that is ready for further testing, such as 3D printing, motion study simulations. Well, this experience has significantly sharpened our skills in SolidWorks and gave us a much deeper appreciation for the engineering that goes into every product. So I would like to thank you, our lecturer, and our friends that has helped us throughout this whole assignment project. Thank you. That is all from my group.